Welcome to Inorganic Chemistry. Today, we are diving into the fascinating world of quantum mechanics to understand exactly where electrons live inside an atom. Imagine trying to find a friend in a massive spherical concert hall. You would need to know their distance from the stage and their direction. Atoms work the exact same way. By the end of this video, you will understand how mathematical equations give atoms their specific sizes and beautiful geometric shapes. Let us get started. Now that we have our concert hall analogy, let us look at the actual physics. In quantum mechanics, an electron's behavior is described by the Schrödinger wave equation. When we solve this, we get a wave function, represented by the Greek letter psi. Because three-dimensional space is incredibly complex, scientists use a clever mathematical trick called separation of variables. This splits the total wave function into two independent, easier-to-understand pieces. The radial wave function only cares about the distance from the nucleus, dictating the size of the orbital. The angular wave function only cares about the direction, dictating the geometric shape. This split is the fundamental reason why atoms bond to form molecules. Building on that idea of splitting the equation, let us look at the mathematical formula itself. The total wave function, psi, is a function of distance r and angles theta and phi. It is simply the product of the radial wave function r and the angular wave function y. The radial part r depends entirely on the principal quantum number n and the azimuthal quantum number L. If n increases, the electron wanders further away. The angular part y depends on L and the magnetic quantum number m sub L. By multiplying these two functions together, we get a complete three-dimensional map of the electron's behavior. This beautiful equation is the foundation of all molecular geometry. Now that we have seen the total equation, let us focus just on the radial part. The radial wave function tells us how the electron's wave amplitude changes as we move in a straight line away from the nucleus. As distance increases to infinity, the wave eventually decays to zero. But before it fades away, the wave can fluctuate up and down, crossing the zero mark. These crossings are incredibly important. They create radial nodes. You can think of a radial node as an invisible, hollow, spherical shell inside the atom where the electrons simply cannot exist. Higher energy orbitals are like onions, with alternating layers of high electron probability separated by these empty spherical gaps. Understanding what a radial node is leads us to how we actually count them. The number of these empty spherical shells is calculated using a very simple formula: n minus L minus 1. Here, n is the principal quantum number, which represents the overall energy level and size of the orbital. But the letter L is the azimuthal quantum number, which defines the subshell type. As the principal quantum number n increases, the orbital gets larger and naturally develops more of these internal layered nodes. If you increase n while keeping L constant, you are adding more hollow shells of zero probability inside the atom. Before we move on to the angular part, let us see these radial nodes visually. This graph plots the radial wave function on the vertical axis against the distance from the nucleus on the horizontal axis. Look at the curve for the 1s orbital. It smoothly decays to zero without ever crossing the horizontal axis, meaning it has zero radial nodes. Now look at the 2s curve. It crosses the zero line exactly once before decaying, creating one hollow shell of zero probability. The 3s curve crosses the zero line twice, meaning it has two radial nodes. This perfectly illustrates how increasing the principal quantum number adds more internal layers to the orbital. Now that we understand the radial part, let us look at the angular wave function. While the radial part dictates the size and internal layering, the angular part dictates the overall geometric shape of the orbital. It tells us how the electron wave behaves as we sweep our view around the nucleus at a constant distance. If the value is the same in every direction, you get a perfect sphere. But if it changes, you get complex shapes. This brings us to angular nodes. Unlike radial nodes, which are hollow spheres, an angular node is a flat plane or a conical surface passing directly through the nucleus, where the wave function equals 0. These directional slices carve the spherical space into the distinct orbital shapes we see in chemistry. This concept of directional slices gives us a wonderfully simple formula. The number of angular nodes is exactly equal to the azimuthal quantum number L. That is it, just the value of L. This quantum number defines the subshell. For example, an s orbital has an L value of 0, so it has 0 angular nodes. A p orbital has an L value of 1, so it has exactly one flat plane slicing through it. This single slice divides the probability into two distinct regions, giving the p orbital its classic two-lobed dumbbell shape. If you increase L, you add more slicing planes, creating even more complex shapes, like clovers for d orbitals. Before we move on, let us see this with a concrete example. Suppose you are asked to find the number of radial, angular, and total nodes for an electron residing in a 3p orbital. This is a classic problem. Our strategy is to first extract the quantum numbers directly from the orbital's name. The number in front, 3, tells us immediately that the principal quantum number n is 3. The letter p corresponds to an azimuthal quantum number L equal to 1, based on the standard sequence, where S is 0, P is 1, and D is 2. These two numbers are the keys to unlocking the entire structure. Now that we have our quantum numbers, let us finish the calculation. We substitute n equals 3 and L equals 1 into our radial node formula. 3 minus 1 gives us exactly 1 radial node. Next, the angular node formula is simply L, which is 1. Finally, we add them together to find the total number of nodes, which is 2. Physically, this tells us that a 3p orbital has a dumbbell shape carved by one planar slice of 0 probability, and it is further split into an inner and outer region by one hollow spherical shell of 0 probability. Let us look at a slightly different example to understand how the angular wave function actually creates shapes in real life. We want to evaluate the angular wave function for a 1s orbital and determine what shape it forms in three-dimensional space. To solve this, we first need the quantum numbers. For any s orbital, regardless of its energy level, the azimuthal quantum number L is always 0. Because the magnetic quantum number m sub L must range from negative L to positive L, it must also be strictly 0. These quantum numbers completely define the angular part of the wave function and tell the equation exactly which mathematical solution to pick. Continuing with our 1s orbital, we look at the exact mathematical solution for these quantum numbers. The angular wave function y equals 1 over 2 times the square root of pi. Notice something incredible here. The angle variables theta and phi do not actually appear anywhere on the right side of the equation. This means the output of the function is just a plain constant number, completely unaffected by which direction you are pointing. Because it has the exact same value no matter what direction you look from the nucleus, this proves mathematically that all s orbitals are perfectly spherical. We have covered a lot of ground today, so let us summarize the most important ideas. The total wave function of an electron is a beautiful partnership between distance and direction. The radial wave function governs the size of the orbital and creates hollow spherical nodes based on the quantum numbers n and L. The angular wave function governs the geometric shape and creates directional planar nodes based on L and m sub L. Together, they give us the complete three-dimensional map of where an electron lives inside an atom. Mastering this concept is your first major step toward understanding how atoms interact to build the universe. Great job today.